In this lesson, we're going to study inverse functions. I've drawn a set of ordered pairs for you, and they are 2, 8, 5, -3, 1, 0. In earlier studies, we called this a relation, But it's more than just a relation. We actually studied this kind of correspondence, and since each one of these x values in the domain correspond to exactly one y value in the range, we actually call this relation a function. I've named this function f. What I would like for you to consider now is reversing the correspondence, basically turning all these arrows around. All right, I reversed the correspondence. I basically took each correspondence and I flipped it. Instead of 2 going to 8, I have 8 going to 2. Instead of 5 corresponding to -3, I have -3 corresponding to 5. And instead of 1 mapping to 0, I have 0 mapping to 1. Now that these entries here are mapping to these entries, then this is no longer my range. This is now my domain. And this is no longer my domain, this is my range. Since each one of these input values corresponds to exactly one output value, then this is also a function. And because we found this function by reversing the correspondence, we're actually going to call this f inverse. And this is the notation for f inverse. It's this exponent of -1. That's how we say f inverse. Okay? So when you hear the word or read the word inverse functions, inverse, think of opposite. Think of reversing this correspondence, okay? So instead of this entry 2 corresponding to this entry 8, it's now 8 that's corresponding to 2. So it worked, basically. Reversing the correspondence worked. We ended up with another function. We called it the inverse of f. But this reversal of the correspondence doesn't always produce another function. Let me show you an example of where this reversal does not work. I've given us a new set of ordered pairs here, 4, 2, 0, 5, and 1, 5. Now, this is a relation because it's a set of ordered pairs, but what I want to make sure you understand is that this relation is indeed a function. I called it function g. Now, do not let the fact that 0 corresponds to 5 and 1 corresponds to 5, don't let that convince you that this is not a function. It is a function. We learned in earlier studies that each x value in the domain must correspond to exactly one y value in the range. And they do. Look at this. 4 corresponds to 2. 0 corresponds to 5. 1 corresponds to 5. So each one of these corresponds to exactly one y value. 0 goes to 5. 0 doesn't go anywhere else but 5. 1 goes to 5. 1 doesn't go anywhere else but 5, right? So this is indeed a function. Now, let's reverse the correspondence like we did a little while ago. Now, reversing the correspondence, notice that instead of 4 going to 2, you have 2 going to 4. Instead of 0 going to 5, you have 5 going to 0. And instead of 1 going to 5, you have 5 going to 1. Also notice that this is no longer your range, this is your domain, and this is no longer your domain, this is your range. This, though, although it's a set of ordered pairs, although it's a relation, this is not a function. The reason why this is not a function is because this domain value corresponds to more than one y value, correct? And so this is not a function. So the question then I have for you is, what must be true of the original function so that when you reverse the correspondence, you get another function? Well, I think it has to do with this correspondence here. 0 going to 5 and 1 going to 5. Although that did not disqualify this from being a function, when we reversed the correspondence, that's when we got into trouble. So these two inputs that have the same output, 0 goes to 5 and 1 going to 5. That's fine, but when you reverse the correspondence, that creates a problem. If you look at the original example that I showed you, function f here, notice that each input has a different output. When that happens, when we reverse the correspondence, we end up finding another function. This will work. This reversal of the correspondence will work as long as each input has a different output. You see, that's not true over here for function g. Different inputs don't have different outputs. These two different inputs have the same output, and that was the problem when we went to reverse the correspondence. When different inputs have different outputs, like function f here, different inputs have different outputs, then you call this function one-to-one. This function is said to have one-to-one correspondence. And notice that when you reverse the correspondence, you also found a new function, right? We called it f inverse, and it is also a one-to-one function because each input determines a different output, right? So every time you plug something different in, you get something different out. This one's also one-to-one. Now, to abbreviate the spelling, instead of one-to-one spelling it out, we can just do 1-1. So this function is also one-to-one, okay? Different inputs determine different outputs. But when we go to function g, now this is a function, don't get me wrong, it is a function, but it's not one-to-one because different inputs have the same output. So we say this function is not one-to-one, and that's exactly the reason why when we reverse the correspondence, we ended up with something that was not a function. Here's a formal definition for one-to-one correspondence. A function is called a one-to-one function if different inputs determine different outputs. Every time you plug something different in, you get something different out. Let's look at an example. So look at this. Determine whether this given function is one-to-one. Now the question is not, is it a function? The question is the function one-to-one? Do different inputs determine different outputs? Every time I plug something different in, do I get something different out? So let's consider some input values, okay? Let's consider some input values. How about f of 3? What would f of 3 be? Well, f of 3 would be the absolute value of 3, which is 3, okay? And then what would let's do a different input, -3. F of -3 would be the absolute value of -3, which is also 3. So I hope you see that these two different inputs have the same output. Different inputs have the same output. In order for a function to be one-to-one, you need different inputs to have different outputs. Therefore, this function, the absolute value function, is not one-to-one. So what's the big idea? Or what's so important about finding out that a function is not one-to-one? Well, if you were to reverse the correspondence like we did earlier, you would not get a function. In other words, you cannot find the inverse function for this function. The absolute value function, because it's not one-to-one, does not have an inverse function. And that's really powerful. So let's actually make a very bold claim and write this in our notes. Only one-to-one functions have an inverse function. This is really important that you highlight this or something in your notes. Only one-to-one functions have an inverse function. If we're going to study inverse functions in this lesson and actually within this entire chapter, then we have to make sure that the function is one-to-one in the first place, because only one-to-one functions have an inverse function. Now we can use something called the horizontal line test to determine whether a function is one-to-one or not. Now, this is very, very similar to the vertical line test that you and I studied earlier. The horizontal line test says that if a horizontal line can be drawn so that it intersects the graph more than once, then the graph is not the graph of a one-to-one function. It might be the graph of a function, but it's not the graph of a one-to-one function. Let's practice using this test. Okay, I've given you some rough sketches of some graphs. Now, each one of these graphs do pass the vertical line test. So all of these are functions indeed. The question at hand is which one of these graphs are graphs of one-to-one functions. So I invite you to pause the video, pause the lesson here, try to apply the horizontal line test to determine which of these are graphs of one-to-one functions. Okay, so I hope you paused the video, the lesson, and you tried this on your own. Here I go. I'm going to draw a horizontal line through this first graph, and I notice that it's a linear function because the graph is a line. FYI, I know that the slope is positive for this linear function. It's a diagonal line going up from left to right. When I draw the horizontal line, now you can draw the horizontal line wherever you want. You notice that the horizontal line crosses your graph only one time. And that's true for no matter where you choose to draw the horizontal line. Therefore, this graph is the graph of a one-to-one function. Now, I want to make a claim that every single linear function will be one-to-one, with the exception of this one here. This linear function is not one-to-one because when I attempt to draw a horizontal line, watch what happens. It crosses your graph infinitely many times. So this one is not one-to-one, okay? So the only linear function that is not one-to-one is the constant function, basically the horizontal line. Every other linear function will be one-to-one. Basically, if it's a diagonal line, it's the graph of a one-to-one function. Yes, it is. But if it's a horizontal line, it's going to fail the horizontal line test. It's not one-to-one. Now, how about this? This is a quadratic function because the graph is a parabola. When you apply the horizontal line test, it crosses more than once with your graph. So this one also is not one-to-one. Now, the font always comes out italicized, so it's funny. Now, this will be true. This will be true for any parabola that goes upward or downward, that a horizontal line will cross your graph more than once. So we can make a claim here. None of your quadratic functions, none of them will be one-to-one. Now, this is a curve for an exponential function. This is something that we will learn in a few days. Now, when you apply the horizontal line test, no matter where you choose to draw the horizontal line, it is only crossing your graph one time only. So this one is indeed one-to-one. This one here, I hope you identify it. This is the graph of a square root function. When I apply the horizontal line test, it only crosses my graph one time. So this one also is indeed a one-to-one function. Again, okay. All right, cool. Now this one is the graph of an absolute value function. And we actually determined a little while ago that an absolute value function is not one-to-one. And here's a visual representation for this, right? So this one is definitely not one-to-one. Okay, absolute value functions are not one-to-one. This is the graph of a logarithmic function, something that we'll study pretty soon. When I apply the horizontal line test, it only crosses one time, no matter where you choose to draw your horizontal line. So this one is indeed one-to-one. Last but not least, this is the graph of a polynomial function. Because there's 1, 2, 3 x-intercepts, This polynomial function has degree at least 3, but it could be more. Anyway, when I draw the horizontal line through the graph, it crosses a lot of times, right? Definitely more than once. So this one fails the horizontal line test quite miserably. So this one indeed is not one-to-one. Now, I want to make sure that we're clear. Only one-to-one functions have an inverse function. That means linear functions whose slope is not 0 have an inverse function. Exponential functions are one-to-one, so they have an inverse function. Square root functions are one-to-one. They have an inverse function. Logarithmic functions have an inverse function. What do not have an inverse function at all, their inverse function does not exist, are constant functions, basically the graphs of horizontal lines. Quadratic functions don't have an inverse. Absolute value functions don't have an inverse. And some polynomial functions do not have an inverse. Okay, so this is very important that you can identify which function has an inverse. Now, let's give a formal definition for an inverse function. We haven't done that yet. Before I show you the formal definition for an inverse function, notice that I've given you a function here, and the ordered pairs, I want you to notice the ordered pairs are 1, 10, 2, 20, and 3, 30. These are the ordered pairs that belong to function f. What I want us to do now is reverse the correspondence like we did earlier. Now, keep this in mind. Function f is indeed one-to-one. Different inputs determine different outputs. So we do know its inverse function exists. Let's reverse the correspondence. So notice that when we reverse the correspondence, we do get another function, and that function is one-to-one. Let's give it a name. Because we started originally with function f, let's call this f inverse, the inverse of f. And the way we do that, again, is by using this exponent of -1, okay, as the exponent there. So this is function f inverse, okay? Now this is the part that I really want you to notice. What are the ordered pairs now? 10, 1, 20, 2, and 30, 3. Notice that the coordinates between f and f inverse have swapped. Instead of 1 going to 10, you have 10 going to 1. Instead of 2 to 20, you got 20 to 2. Instead of 330, you got 33. So instead of x going to y, you have y going to x. Okay, with that being said, let's write down the formal definition for the inverse function. Here it is. If function f is a one-to-one function consisting of ordered pairs of the form x, y, the inverse of f, denoted f to the negative first, is the one-to-one function consisting of the ordered pairs of the form y, x. So notice that everything switches. The correspondence, instead of x going to y, now you have y going to x. And not only that, remember what used to be the domain is now considered the range, and what used to be the range is now called the domain. Please notice this relationship, this reversal or opposite thing going on between a function and its inverse. All right, determine whether each of the following functions is one-to-one. If it is, find the equation of its inverse. Here's the first function. F of x is equal to 6x minus 4. Now, is this function one-to-one? Well, consider its graph. This is a linear function whose graph would be a line with slope positive 6 and y-intercept negative 4. We said earlier that any diagonal line would pass the horizontal line test and therefore be one-to-one. This is a diagonal line. As long as the slope is not 0, it'll be a diagonal line. So because this is a linear function with non-zero slope, it's one-to-one. So make sure you have this in your notes. Because this is a linear function whose graph is aligned with non-zero slope, that's important. we know it is one-to-one. You know, it's tempting to say every linear function is one-to-one. I guess you can say that as long as you say, with the exception of the constant function, you know, the horizontal line. That's also a linear function. That's a linear function whose slope is 0, right? Horizontal lines. And those are the only exception. Those are not one-to-one. All right, so we know that its inverse exists, so let's go and find it. All right, so please watch these steps. The first thing I'm going to do, now pay close attention, please. The first thing I'm going to do is replace f of x with y. We learned a while back that f of x represents y. They're interchangeable, right? And then the next thing I'm going to do is swap x and y, swap places. Now you can imagine why we do that, because we just defined what an inverse function is. Instead of x going to y, you have y going to x, that reversal of the correspondence, right? And then to wrap this up, what I advise us to do is to solve for y. So isolate y, that is. So I'm going to add 4 to both sides, and that gives me x plus 4 is equal to 6y. And then divide both sides by 6. And then I have y isolated. Now I have y is equal to, right? Because 6 divided by 6 is 1, so y is equal to, I'm reading right to left, y is equal to x plus 4 over 6. X plus 4 over 6. The last thing you're going to want to do is replace y with function notation. Now you started with f and you just found its inverse. So let's use this notation. F inverse of x is equal to x plus 4 over 6. This is the inverse function for f, all right? Please notice the steps. You may want to add this in your notes, okay, if you want. The first thing I did was replace f of x with y. I'm not sure if you're writing this down or not, but step 1 would, if you're a step-oriented person, step 1 would be replace f of x with y. Step 2 would be interchange x and y, right? Interchange, or you can maybe use swap places, you know, swap x and y. And then the last step is solve for y. Solve for y. Oh, I guess that's not the last step. The last step would be use function notation in your final answer. Okay? Now, before we move on, I do want you to notice one thing. Notice that f is multiplying by 6 and then subtracting by 4. Multiplying by 6, subtracting by 4. F inverse is adding 4, dividing by 6. Do you see the relationship? Multiplication by 6, subtract 4. Add 4, divide by 6. The operations that F inverse uses are the opposite operations. See over here, you see minus 4, plus 4. Multiply by 6, divide by 6. Isn't that interesting? F inverse will undo everything that F did, right? All the operations that F performed on your input, F inverse will undo all of those operations in the reverse order. All right, let's find another inverse function. All right, the next function is the cubic function. This is our most basic cubic function. Do you remember what the graph looks like? I'll remind you really quickly. The graph looks something like this. This is a quick sketch, okay, everybody? The graph of this basic cubic function looks like this. We graphed it in earlier lessons. Now, if you apply the horizontal line test, you see that no matter where you draw the horizontal line, it only crosses your graph one time. So therefore, this function, because it passes the horizontal line test, it is indeed one-to-one, okay? So we do know its inverse exists. Okay, here we go. Let's replace f of x with y. And now let's swap x and y, or interchange. And now let's solve for y. Now, in order to solve for y, you need to undo that third power, the cubing action. And in order to undo the cubing action, you should take the cube root, because the cube root will cancel with the cubing, right? Those two will cancel. And so what you're left with is y is equal to, I'm reading right to left, y is equal to the cube root of x. Using function notation, we would write f inverse of x is equal to the cube root of x. This is the inverse function for f. All right, to wrap up this lesson, we're going to find the inverse function of the one-to-one function that I'm about to give you. We're going to graph this function, also graph its inverse, and something called the line of symmetry, all on one coordinate system. All right, here we go. The function that I want you to consider is f of x is equal to 1/2 x plus 1. The first thing they want us to do is to find the inverse of this function. Now, does the inverse even exist? Well, it does as long as f is 1-to-1. Is f 1-to-1? You should say f is 1-to-1 because its slope, it's a linear function whose slope is not 0, right? So as long as it's a linear function whose slope is not 0, we do know it's 1-to-1. They actually gave it away in the instructions, right? They said find the inverse function of the 1-to-1 function there. So they're telling you from the get-go that this function is 1-to-1. But I want to make sure that you understand how to confirm or verify that the function they gave you is indeed 1-to-1. All right, so let's graph this function, its inverse, and the line of symmetry on one coordinate system. But before we do that, let's find its inverse. All right, here we go. So the first thing we're going to do is replace f of x with y. And then we're going to have x and y swap places or interchange, right? And then we're going to solve for y. The first thing I'm going to do to solve for y is subtract 1 from both sides. And then finally, I'll just multiply both sides by 2. Let me show this step. I'm going to multiply this side by 2, multiply this side by 2. Okay? Now, whenever you multiply a number by its reciprocal, all you get is 1. So on the right side there, you only have 1y. And so then this is y is equal to, now again, I'm reading this from right to left, y is equal to, and then I'm going to distribute this 2 here to give me 2x minus 2. Now, I should write this using function notation, so I'll write it as f inverse of x is equal to 2x minus 2. Now that we've found this inverse function, they want us to graph both functions on one coordinate system, okay? So I'm going to get rid of some of the work that I have on the screen so that I can have enough room to show this for you. All right, so we have both of our functions here. Which one should we graph first? Well, I recommend that you graph the given one first, just in case you made a mistake with finding f inverse. So graph this one first. Remember, this is a linear function, so it's a line whose y-intercept is 1, so that's where I'll start, a y-intercept of 1. And then the slope is 1/2, rise over run, so go up 1 to the right by 2. If I go up 1 and to the right by 2, I end up at 2, 2. I can equivalently go down 1 and to the left by 2, and that will drop me off at -2, 0. Now this is the graph for f. Okay, everybody? I'm going to label this f. Now, let us graph f inverse. Now watch this, please. Notice that these ordered pairs that belong to f are, now going from left to right, f has the following ordered pairs: -2, 0. It also has 0, 1, and it has 2, 2. Now please remember that when we defined an inverse function, we said that if f is a 1-to-1 function consisting of ordered pairs x, y, then f inverse is a 1-to-1 function consisting of ordered pairs y, x, right? So you have that swapping, reversing of the correspondence happening. In other words, what I'm trying to get you to see is if -2, 0 is on the graph of f, then 0, -2 lives on the graph of f inverse, right there, okay? So if this point here is on the graph of f, all I have to do is swap these coordinates to get this point that's on f inverse. F inverse will have the points 0, -2. Let's go ahead and swap these two coordinates, right, to get the point that it is on f inverse. So instead of 0, 1, you're going to have 1, 0. Excuse the sloppiness, but 1, 0 would be that point. And this one, instead of 2, 2, you'll have 2, 2. So this point actually lives on both of my functions. And so the graph looks something like this. Okay? This is the graph of f inverse. Okay? Notice that they intersect, and they intersect at 2, 2. The graph of a function, the graphs of a function and its inverse do not always intersect, but in this case, they do. Now let me show you what's called the line of symmetry. But before I do, I just want to reiterate how I graphed f inverse. I took the points that are on function f and I just swapped the coordinates. Just swap the coordinates and then you get the graph of f inverse. Okay, the line of symmetry. Now the line of symmetry is always y equal to x. This is a line, it's actually called the identity function. Y equal to x is a line whose slope is positive 1, right? Positive 1, and y-intercept, since it's not written, is 0. Let's graph this line of symmetry and then I'll talk about it further. Now because this is not part of f or f inverse, I'm gonna draw the line of symmetry using a dashed line. So it goes right through the origin. That's the y-intercept of 0, 0. It goes through, the slope is positive 1, right? So rise over run will be 1 over 1. So go up 1 to the right by 1. If I go up 1 to the right by 1, I end up at 1, 1. If I go up 1 to the right by 1, I end up at 2, 2. And then I'll end up at 3, 3. And then I'll end up at 4, 4, and so forth. If I go down 1 to the left by 1, I'll be at -1, -1. And then -2, -2. And then -3, -3, right? So then the identity function looks like this. Now, this is always your line of symmetry. Now, this is the very, very, very important thing that you should remember about the line of symmetry. The graph of any function and its inverse will be mirrored images of each other with respect to this line. In other words, the line of symmetry acts like a mirror. And what you see on one side of the line of symmetry, you get the mirrored image over here for the inverse function, right? So for example, -2, 0, its mirrored image across the line of symmetry would be 0, -2. These 2 points are mirrored images of each other with respect to this line of symmetry. 0, 1, and 1, 0, these 2 points are mirrored images of each other. And you can see this with every point on each of these lines. These lines are mirrored images of each other with respect to the line of symmetry. The line of symmetry is always the identity function y equal to x. One last thing I'd like to say is that although the graph of f and f inverse are not guaranteed to intersect every time, if they do intersect, what's really interesting is they will intersect on the line of symmetry. So notice that they intersect right here at 2, 2, and that point is on the line of symmetry. So if a function and its inverse intersect, they will intersect on the line of symmetry. Let's add some of these statements to our notes. Okay, so add this to your notes, please. The graph the graphs of a function and its inverse function will always be mirrored images of each other about the line of symmetry. Okay? And then if the graph, that's a key word, if the graph of a function and its inverse function intersect, then the point of intersection will occur on that line of symmetry. Okay? All right, everybody, this concludes this lesson. I hope you learned a lot, and I hope you had fun doing so. I'll catch you in the next lesson.